Welcome everyone. I hope you're all doing well. Thanks for being here today, and feel free to say hi in the chat. It'd be good to hear from you all. We've got a nice A-level topic today to look at. So welcome if you're here. I'm just going to make sure I can see the chat and welcome you all as you join. So that's great. Hopefully the link's there as well. And we're going to get started shortly. But as I said, I hope everyone's keeping well and you can all hear me okay and we're good to go. Feel free to ask any questions or submit some answers in the chat as we go as well. I'm going to just share my slides now and we'll get started shortly. That'd be great. So welcome if you've just joined, and please do say hello, and as I said, any questions as we go, that'd be great to hear from you. Cool, I'm going to share my PowerPoint just as we're about to start. And hopefully we'll all be able to see that. Welcome. Okay, excellent. So do let me know that you can see that and that you're here. It's great that you've joined. Welcome. Please say hi in the chat. Hopefully you can all see my screen now. I'm about to work through differentiation from first principles today. And it's lovely to see some of you joining right now. I hope we've all had a nice weekend and everyone's keeping well. This is a big A-level topic. So differentiation, as I'm sure you're aware, is a massive part of the A-level. It's the sort of first part we look at of calculus. Welcome, lovely to see you all saying hi. That's great. All the messages are coming through now on the chat. So welcome everyone. We're going to look at this topic today. Now, this is a really important part of the A-level course. And actually, when the GCSEs changed in the A-levels changed in 2017, this was kind of added in. So differentiation from first principles, I think, is a really important to look at because it was added into the A-level. It used to be differentiation has always been on there. This is a really key topic, but I didn't personally meet first principles until I went to university. So this is such a crucial topic to look at, and it's kind of the background of how differentiation works. Lovely to see so many of you commenting and saying hello. I hope we're all doing well. I'm going to get started, but as I said, a really important topic, and I think for those of you that have seen this before, you may be aware that schools perhaps put emphasis on this because it's quite new to the course. There's this sort of feeling that it's more likely to be examined or there's more of a worry about it. But it's a really nice topic just for your general understanding of differentiation. So I'm really keen to crack on with this today with you all. If you can let me know in the chat if you have seen this idea before, that would be great. For some people, this might be revision, and for others, this might be new content. So please let me know. It's more differentiation from first principles, but you can look at integration in a similar way using the summation of kind of almost like trapezium rule, infinite kind of a summation of small strips that add up to make the area. So in a similar way, you can do a very similar thing with integration. Excellent, great. So some of you are currently looking at this. But yeah, it's a little bit different. We generally refer to differentiation from first principles, but some brilliant questions there. We'll get started anyway. So I'm Max, I'm head of maths at Snap Revise, and I've been teaching maths at A-level GCSE and below for the last 4 years. And it's been a really good time actually to see the courses change over. The A-levels changed quite in a major way really in that time. And the GCSEs have kind of changed a lot. And obviously we're kind of living through a really strange time in terms of education as well. But in terms of the content that we've been able to teach and look at, I think the syllabus is still equally as exciting, but also at the same time, there's a real breadth to the maths. So all of you doing A-levels, I'm sure you can appreciate that this is actually, there's so much, it's so multifaceted at A-level with the mechanics, stats and pure. So there's a lot to kind of keep track of. Excellent. So I'm going to move on and just mention that the following. So if you're unaware about this, so free account for one will be given away. If you follow us on Instagram and share a picture of our web class on your story and tag Snap Revise, we'll be giving away a free account. And there will be a coupon code at the end if you stay tuned for that. And there'll be a discount for you there, hopefully. So if you keep watching, and obviously it'd be great to hear from you in the chat in terms of answers and questions, obviously, as we go, that would be great. Lovely. I'm going to carry on. And again, welcome if you've just joined. It's great to see so many of you in the chat here saying hello and commenting. Please do ask questions and comment throughout. It'll be great for me to see how we're finding this as we go. So this is very much an A-level topic. It's great for sort of building your understanding of differentiation. But as I've said, I know for some people this is very new, and for others this is a topic they're revising. So we're going to look at what is meant by a limit. That's a really important idea. We're going to sort of recap binomial expansions because they can be quite important as well. And we're also going to look at graphically and algebraically what we're doing when we differentiate by first principles. I won't be differentiating exponentials, logs and trig functions, although this is something that's extended on particularly the trig side of it in year 13. So this is the kind of basis of first principle differentiation. So excellent, we'll get cracking, and as I said, welcome if you've just joined. Just to start with, just to kind of go over what we should know as kind of prerequisite knowledge. This session will probably be just under an hour now from now, and we'll be wrapping it up, but we should get through all of this content through in this web class, so hopefully that's helpful for you. So gradients, we hopefully know even from GCSE that this is referring to sort of the steepness of a line. So the gradient is effectively, we're looking at a steepness. And so if we inspect different points on the graph and we look at what the steepness is doing for obviously a quadratic graph, you can see that on this part, we've got a positive gradient, here we've got a negative gradient, and here at the turning point, the gradient is actually flat, it's 0. So where we have a real difference from GCSE is we dealt with straight line graphs, y equals mx plus c, where there was a constant gradient. And so you hopefully remember from GCSE and potentially from physics, for those of you that have done it as well, that we're essentially dealing with a change of y and a change of x. And you might have learned it as rise over run. Sorry guys, my pen's been a little bit funny here. But hopefully the annotations will come through in a second. So differentiation, for those that have met this, this content will feed into A2, but it's largely the basis of first principles. You might have noticed that the notation for differentiation, is we use f dash of x. Oh, apologies guys, the pen's been a bit funny, I'll just get that sorted. Do let me know if you've seen that before. So let's have a little look, and that will hopefully be kind of useful for you there. And then the gradient dy dx, if we're using function notation, we use f dash x, and if we're using y, we use dy by dx. Okay, good. So what we've got is if we differentiate a function, for those that have done this in year 12, if we have something like x to the power of n, then the derivative of that, which I can denote as d dx, let me just flip this round so hopefully the writing will come through a little bit clearer. D by dx, then what we would have is we times by the power and drop the power by 1. So hopefully those of you that have seen differentiation before will know that that's a thing, and you'll recognize that kind of idea. Who has done binomial expansion? Is that something we've seen before? Yeah, excellent. Thanks for that. Well done. And thanks for writing that in the chat. Who has seen binomial expansion? So binomial expansion sort of deals with expanding brackets like this. Lovely. Okay, excellent. So you may have used it to expand a bracket like a plus b to the power of n, and you might write that in ascending powers of n or ascending powers of a or b, depending on how you've done it. But it basically allows us to use combinations to expand brackets. Well done, and that's great to hear. Sorry guys, I'm hoping to get this pen sorted shortly, and that should then become a bit clearer. Let me just clear that off. B n minus r. And then the end choose are, we've hopefully seen this button on the calculator. Yes, we're going to look at limits, absolutely. And it's quite a new idea, as I mentioned, for the A-level, so we will look at that specifically. And this is something that we would have seen, hopefully, if we've met first principles before. Right, so as I said, the differentiation and first principles is common to all exam boards. So now all of the A-levels are doing differentiation from first principles, and we have to understand this idea of a limit, which some of you have asked about. So that's great. And that will be whether you're OCR, AQA, EdExcel, any of the boards there will be using limits. So this absolutely, yes, definitely, year 13s will need to know this stuff because it does come back up. So I'm going to talk through what a limit is. I know I've had a question about that already. So the limit of a function f of x as x tends to a is basically the value. Hang on, sorry guys. Is basically the value that f of x is getting closer and closer to. So if I, for example, say that this value is 1, and I draw in the asymptote here, can we see that the limit of this function as x tends towards infinity, what is the limit of the function? So if this is the function, as x approaches infinity, what is the function tending towards? What is the function approaching as an asymptote? Any suggestions? So if we look at this function, just in general, as x gets bigger and bigger, then what we've got here for this particular function is that the function is tending towards this value of 1. So as x tends towards infinity, the function is approaching 1 as the output. Now, this is just generally what limits are because they kind of tie in with asymptotes. So it's a really important idea. Excellent, thank you, well done. And what some of you might have noticed is that as x approaches 2, what we've actually got is this vertical asymptote. So can anyone tell me that as x approaches 2, what the function here is approaching? Any suggestions with this one? So as x, the input value, here we can see at 0, at 1, as it approaches 2, what is going on? Excellent, yeah, really good. Since it's an asymptote, x is sort of shooting up towards infinity. So for that one, the limit would be infinity. It's tending towards infinity. Very well done. Thanks, guys, that's brilliant. So this idea of a limit goes beyond calculus and goes beyond first principles. So this is great. If you've kind of worked out that essentially it's what the asymptote is doing in this situation, then that's what we're looking at. I'm just going to swap pens because I think this might hopefully work a little bit better, but apologies for that. Let me just swap this round. Lovely. And yeah, absolutely right. For those that have said that there, let me just see if, there we go. So is the, whoops. Yeah, excellent. Okay, so I'm going to move this on and we're going to look at finding limits algebraically. So again, if you've done this before, you'll hopefully realize that we can sort of split the limits up. So the notation for limit, lim as x tends towards a for this function, we're going to have a little look at now. So have we seen before, for those that have done it, that we can split the limit up into 2, where we have the limit of f of x plus the limit of g of x as x tends towards a for both. Who has seen that idea before? And apologies again, guys, the pen has been a little bit weird today, which isn't the best, but hopefully that's kind of vaguely clear. Excellent. Yes, good. So in year 12, some of you will have already done this. So what we're going to look at for this actual example, because this is a typical question, you could have, yeah, essentially you can split it in that way. the two parts of the function, just like you can with other parts of differentiation. So for this question here, what we can do is we can kind of look at what's going on as x tends towards 0 in each of these. So if I were to do that for this question, I've got a quadruple bracket. So I might want to expand that. Now, I don't really want to expand a quadruple bracket long ways. So what you would use here is your binomial expansion. So for those of you that have done this before, hopefully you can fill that in. And we're going to have limit as x tends towards 0. And I'm going to try and expand that using binomial. So 81x to the 4 plus 216. And you can see how this is going to start to bring in other skills that you've used in earlier chapters. Plus 216 x squared. For those of you that have done this, and feel free, if you have got access to a copy of the slides, to make a little note of this. That would be brilliant. 96x plus 16, and then we're going to minus 16 from all of that. So hopefully that's all come through okay. And it's all divided by x. So we're just going to look at how limits work for this scenario, because they are a little bit abstract. So if this is new to you, this might look a little bit kind of crazy, because it is obviously not really covered at GCSE at all. But you're essentially expanding a quadruple bracket, tidying up algebraically what you've got, and we're going to look at what the limits are doing. So here, what we're left with, because we can cancel through by x, and also the 16, take away the 16 will sort of cancel anyway, we get left with the limit as x approaches 0. And please, if you've seen this before, do work ahead of me and let me know what you get. 81x cubed plus 216x squared. I'm just dividing through by x as it was in the question. 216x plus 96. Now, if x is approaching 0, if x is getting smaller and smaller towards 0, excellent. What's going to happen here essentially is that this is going to approach 0, this is going to approach 0, this is going to approach 0, and the standout bit is this. The whole thing is going to approach 96. So as x approaches 0, basically x is becoming negligible. It's becoming more and more irrelevant, and we're looking at overall what the function is tending towards. And now the function here overall is tending towards 96. So the limit of this would be 96. Hopefully that's sort of clear, but if you haven't seen this before, obviously it would be great to see this in the context of differentiation. So limits, a little bit abstract in the idea, is we're saying as we make x get smaller and smaller to 0, what is happening to the value of this expression? It's approaching 96. So let me know if that makes sense to you, even if this is quite a new idea. Brilliant. Right, I'm going to just move that on quickly. So if you could give me an indication in the chat, 1, 2, or 3. Obviously, if you've seen it before, this might be fine, but just to give me a sense of where we're at this point, and we'll do a few questions together. Cool, excellent. Don't worry, be honest, that's fine, and we'll go from there. And what we'll do is we'll look at a few exam questions where we're asked to actually use limits, and we'll try and make sense of it from the context of these questions for those that are perhaps still struggling a little bit. Lovely, cool, but please do ask the questions as we go, and I'll try to answer them as we go through. So here's a few questions that you're welcome to try now. The first one says, evaluate the following expressions for the limits of x approaching 0. So as x approaches 0, what do you think is going on with each of these expressions? And they are a little bit weird because it's not the sort of scenario that you can always necessarily just plug into your calculator. So for the first one, what do we think is happening for this one as x approaches 0? So as x gets bigger, smaller and smaller towards 0, the denominator is turning into a really tiny decimal. So if you do 1 divided by a really tiny decimal, are we happy that we get a really big number out? Because you're essentially saying how many times does this tiny decimal go into 1, which will be huge. So if you do 1 divided by 0.00001, it will be a massive number. So if you were to type this in your calculator, it will say math error, undefined, or something like that. But actually, we need to understand what that means in terms of what the value is approaching. So if you put a really small number close to 0 in, you'll get a really big number out. So actually, as x gets smaller and smaller towards 0, the number just gets bigger and bigger. So it's actually, for the first one, interestingly, the limit as x approaches 0, the actual overall thing, absolutely well done to those that have suggested it in the chat, is actually infinity. It's actually growing to become a massive number. So it will actually be positive infinity, absolutely, and well done if you got that. Lovely, and thanks for the comments, guys. So as x approaches 0, the whole thing is approaching infinity, and well done if you got that. Please do feel free to work ahead and try some of these later ones that I'm going to talk through now. So for the second one, let's have a little look, and if you've done it, please let me know. Now, we might want to start by first expanding that bracket out. So the limit as x approaches 0 of this, x squared, 2x squared minus 2x to the minus 2. And what we're going to get here, has anyone expanded that? Do let me know if you have. And remember just your rules for powers if you're expanding that one there. And what we're going to get is we are going to get that that's the same as the limit as x approaches 0 of 2x to the 4 minus, and this will become 2. Is everyone happy with that? So if I expand that bracket out, I get 2x to the 4 minus just 2, because x squared times minus 2x to the minus 2, if you add the powers, or if you treated it as a fraction as well, that would work. So that's what we have there. Now, as x approaches 0, as x gets smaller and smaller, this bit here is essentially, sorry about that, is going to disappear. That's going to approach 0 as well. And what we'll have is that the whole thing will be approaching minus 2. So the limit of this function as x approaches 0 will be minus 2. Lovely, brilliant. So what we'll do now is we'll have a little look at the next one, because this ties into more what we're going to be doing with differentiation. So for this third part here, for this third part of the question, please do let me know if you've got an idea for this one, because this is a little bit more involved. So part 3, what we've got is we need to sort of do the binomial expansion of the first bit. So if I work out what x plus 2y cubed would actually expand to, I'd get x cubed plus 3x squared times 2y plus 3x times 2y squared. Whoops. That's lovely. Thanks, guys, for the comments. I'm going to try and power through this so we can get on to more of the actual differentiation here. 2y cubed. And so what we can do with that is look at subbing it in back into here, taking away 8y cubed and then dividing through by x. And I believe that the limit of that is going to be 12y squared. But that could be perhaps a question you work towards afterwards. So we can crack on with this differentiation now. So it'd be good to see it in the context of differentiation. I would like to just shed some light on how this works in terms of the graph, because we don't always get the chance to do that in school when we're learning it as a process. So what we've got here is the gradient of the tangent at a point of the curve is essentially equal to the limit, and I'll annotate the graph to show you that. The limit, oops, let's do it down here. The limit of the gradients of the chords. So the limit of the gradients apologies for the pen messing up here, guys. I'll try more to annotate on the diagram and you can kind of make a note. So essentially what I'm saying is if we take the chords of different points, and well done for those that are sort of seeing what we should be doing here. If we look and we make the kind of chords smaller and smaller to essentially close the gap, what we're doing is we're tending towards the true gradient. So you might be thinking, so at this point, the gradient would be 0, but we might want to do that at various points on the curve. So what we're doing is we're looking at the limits of the gradients. And as we kind of close the gap, the change of y over change of x is essentially what we're finding. And we're going to explain this a bit more on the next slide. So what we're doing is we're producing a gradient function. So what we've got here is we're going to look at first principles basically from scratch. So the derivative f dash of x is essentially the limit as h, the limit, oh apologies guys, this pen is looking a little bit knackered at the moment, the limit as h approaches 0. Yeah, and well done. So some of you straight away have said that for this function, I know what the derivative is, and that's brilliant. And some questions will ask you to just differentiate. However, if you're asked to do it from first principles, you have to go through the motions of this. And the good thing is you can sense check what the answer should be. So let's have a little look. So looking at the limit as h approaches 0, now this formula is generally given in the formula book, but I want to just explain the context of it. So what we're looking at is the limit of f of x plus a small change subbed into the function minus just the output of f of x all over h. Now what this effectively is, what we've essentially done here is I've put f of x and put x in and spat out a value, that's like your y value, and then I've put a small change x plus h, and that spat out a y value, f of x plus h. And then we know that the gradient is the change of y over the change of x. So essentially for that scenario, it's f of x plus h minus f of x, the outputs of both, divided by the small change h. And we're making h smaller and smaller to essentially close the gap and algebraically limit it to what it's doing at that specific point. So who has seen that actual sort of formula for first principles before? Because you may well have seen it, but you might not have had the chance to question, why is it f of x plus h minus f of x over h? What are we doing? We're essentially looking at the outputs, the change of y over the change of x, and saying, if I make that change smaller and smaller and smaller, I'm actually pinpointing it. And what's really cool about this is, although it's quite abstract, it essentially tells you what the whole thing is converging towards doing, and then gives you a function for what's going on at that point. So what we would get here is, for this function here, x cubed, we're going to take the limit as h approaches 0 of x plus h cubed minus x cubed all over h. Please let me know, can we see how this is essentially a direct application of what we've got there? The function is a cubing function. I'm doing x cubed, but I'm subbing in h and then taking away the normal output. So what we've done is the function is a cubic function, but I've plugged x plus h into it. Now I've got a bit of work to do here. This isn't the end of it. That's not obviously the answer. But what we're doing is we're relating that formula that we're kind of given up here to the scenario we've got. And the scenario we've got is x cubed. So what I'm going to do is I'm going to use binomial expansion to expand this x plus h cubed bit. And what I'm going to get is I'm going to come out with the limit as h approaches 0 of x cubed. And if I do the binomial expansion of this, hopefully we're happy. It's going to be quite a few bits to it. 3x squared h plus 3x h squared. And please do this yourself if you've seen this before. Let me try and neaten that up. 3x h squared plus h cubed minus x cubed, and all of that is over h. Okay, so what we would have is we're going to end up, this is basically going to boil down to the limit of h approaching 0 of 3x squared, yep, because that will be cancelled with that. We're going to get 3x squared h plus 3x h squared plus h cubed all over h, and then if I cancel the h's, I essentially end up with 3x squared when h goes towards 0, because as h goes towards 0, what will happen is this bit will go, this bit will go, and this will come out as the limit. So 3x squared. Now, very well done to those of you that said, I know that x cubed differentiates to 3x squared because I times by the power and I drop the power by 1. You're absolutely right, and you want to be doing that because what it does is it lets you say, I know what the answer should be. And if this was a 1 mark throwaway question that wasn't first principles, I should be able to do it. But if they ask me first principles, there'll be more marks up for grabs, but they want to see this process worked through. They want to see you plug in this small change with h, the difference in the outputs over the small change h there, and then taking limits to produce that derivative you know that the function is tending towards. So very well done, and hopefully that does make sense to you there, but we'll do some more practice of this. And thank you again for the comments and following along through this. If this is new to you, I appreciate that this might be quite a strange idea. It was very abstract the first time I saw it. So how do limits give the derivative? What they're basically doing is if you imagine tangents or chords to the curve and you're narrowing the gap down so that essentially they are just the steepness of that point on the curve, you're essentially giving the function that those steepnesses are following. So this graph x cubed, the function that describes its steepnesses is the graph 3x squared. The values that come out of that actually tell you what the steepnesses are doing. So the trig ones are more of a year 13 thing, so this will be largely focused on the general bit of first principles. If you can give me a little update of how you found that, and then what we'll do is we'll do a very similar exam style question worth 5 marks where we go through another very similar scenario. So let me know 1, 2 or 3, just roughly how we're feeling after that. I know, as I said, there's a mixture of people that have done a lot of this and others that have never done this before. So I really appreciate the comments and like a little indication of how you're getting on. Thanks very much. We're gonna keep going, guys. So the next one we're gonna look at here is an exam question. I don't know if I'm blocking the amount of marks there, but it is worth 5 marks, and we want to differentiate the function x to the power of 4 from first principles. So those of you that say, well, okay, I know what that should be, times by the power, drop the power by 1, that's great, but that won't be the 5 marks. That's just going to help us check at the end. So to differentiate this from first principles, I'm going to get the pen ready. So we're going to use the formula from before. So f dash of x, remember we said is going to be equal to the limit of h approaching 0 of f of x plus h minus f of x all over h. That's great. And for this one, and well done, those of you that know the answer should be 4x cubed. That's lovely. And this is what we're working towards. So we're going to do x plus h to the 4 minus x to the 4 all over h. And I should really write limit in front of that. Squeeze that in there. Limit as h approaches 0. So what I'm basically doing is I'm putting in x plus h, x plus a small change plugged into the function and see what it spits out, minus just x plugged into the function to the power of 4, and then dividing it by that change in x, like change of y over change of x is effectively the gradient. And then what we're going to do is basically look at what the limit of this is, look at what that whole thing boils down to as h gets smaller and smaller. So for those of you that have done binomial expansion before, please do give this a go and see if you can kind of hopefully beat me to that. But expanding that quadruple bracket there, you're going to get x to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4. That's the massive expansion of this bracket, which is a topic in itself. And then we're going to minus off the x to the 4 that we were doing in the change of y, and the change of outputs, all over h. Now, what we're going to get here is, and this generally happens, so this is sort of a general thing that happens in the method, that bit will cancel, and then what we'll do is we'll try and divide through by h. That'll become 3, that'll become 2, that'll become 1, and that'll go. And what I'll get is basically, yeah, so if you do it directly, you haven't done it by first principles. So this is the skill they're checking. And that's why this is crucial that you know this method, because as I said, this is new to the A level. So I suppose there is this kind of idea that, okay, maybe it's more likely that they actually do want to test this then. This seems like something that we should focus on because it's been added in. So what we'd get is this would boil down to 4x cubed plus 6x squared h plus 4xh, and then h, and then h squared, and then plus h cubed. And what we're going to have here is the limit of that, as we should want, is basically as h goes smaller and smaller towards 0, that gets more and more negligible and gets closer to 0, that gets closer to 0, and that gets closer to 0. So the limit of this function is 4x cubed, which many of you said at the start should be the derivative. That should be the gradient function. So this is hopefully really kind of a clear sort of similar method to what we just did, whereby we're subbing in, we're doing the binomial expansion to see what x plus h subbed in gives us, and then we're tidying it up and using limits. Now, I know if you've not done a lot of limits before, which prior to this year you probably haven't, it's very abstract and weird that you're sort of saying it goes towards 0, so all these things become 0. But that's what we're doing. We're closing a gap and looking at ultimately what is the thing doing, what is the function that it's following. So this is relevant for AQA, EdXL, OCR, any of the boards now do cover this stuff. Brilliant. Right, we're going to do another question here, another exam style question worth approximately 5 marks. So please do, you might want to firstly in your head differentiate it and go, right, I know what I'm aiming for. I know what the answer should be. So what we're going to do is we're going to do this one by first principles. So we're going to do the limit as h approaches 0 of this function. Now, this is where it gets a little bit weird because the function is this. So if I sub x plus h in as x, I sub it in a couple of places. So what I'm going to get here is I'm going to get 7x plus h squared minus 6 lots of x plus h. Oh, not x plus 3. X plus h minus 3. Then I'm going to take away the actual function with just x subbed in. So it is the same process, but it just looks a little bit more involved. But it's exactly the same. You're subbing x plus h into the function, and then you're just subbing x into the function, and you're dividing it by the small change in x, which we call h. And we're going to look at what happens with this one. So yeah, absolutely, this feeds into second year, this feeds into the year 13 A-level content as well, and you build on it. So hopefully that's clear, but please do ask a question if you're unsure as to how I plugged in x plus h. Cool, and well done to those that know what we're aiming for here. Now, if I expand that all out and tidy it up, and I'm going to get minus 6x plus 6h minus 3, and I'm going to minus from that 7x squared. So it feels very tedious, and as you can see, that's why this is more marks, especially when we can kind of just work out what essentially it is going to be as the answer. So then the limit as h approaches 0, this is going to tidy up. So when we expand that out, we get minus 6x minus 6h minus 3. So let me do that. And then if I take away this, the 7x will cancel there. Minus 6x will plus it and cancel that. And then the minus 3 will plus it and cancel that. And so what we get left with is 14xh plus 7h squared minus 6h all over h. And if I cancel accordingly, what I end up with is the limit as h approaches 0 of 14x plus 7h minus 6. Now, as h goes to 0, that disappears. So my answer is 14x minus 6. Okay, so please let me know if that made sense, if that was clear what I did there. I know there was a lot of cancelling to do. Yes, exactly. Well done for that question. You are essentially just subbing x plus h in to whatever the function was instead of x, and taking away x subbed in. So what you've done is you've looked at what would happen if I put x plus h in, what would happen if I put x in, do the difference of the outputs over the small change of x, which we call h. And then that essentially is change of y over change of x in this sort of limit way. Absolutely, you can do it in a more simple way, in that you could just go times by the power, drop the power by 1. But you cannot do that for this question if it says from first principles, because you won't get the marks. So this is, as I said, a new skill. It's much kind of higher level, rigorous maths that's a little bit abstract in style, but has been added to the A level to check we understand that we can look at what the function is tending towards doing. And that is what a limit is. That is what we're looking at doing here. So really good questions, and thanks for that, for those that have come through. I'll keep an eye on the chat as we go. That's great. So we'll do a very similar one now to see that it's kind of a little bit more scaffolded, this question, but it will sort of test that we can sub in x plus h in the correct way. Yes, so absolutely, you should just be familiar of what to do. I think most boards, the formula is given in the formula book, but I think it actually really helps if you've practiced this, you'll basically memorize the formula. It's easier than you think, the f of x plus h minus f of x over h, but you do certainly need to know how to do it. That's great. But yeah, as I said, the more, like a lot of the A-level topics, if you've done enough practice, it won't even feel like a task memorizing it, because you will have used it so much that it just sort of stays in your head then. So that's a good judge of, have I done enough practice? Is it an effort for me to memorize it, or do I just know it now? So what we're going to do, we'll do this other question here as a nice sort of rounding up of limits and first principles. Thank you again for all the work you guys have put in so far, and let me know in the chat. That's great. And I appreciate that this is a full-on, difficult A-level topic. So let's have a little look. Given that f of x is x squared minus 4x plus 2, so we've got this quadratic, I want to find f of 3 plus h. And you might think, okay, that's a bit random, like, why would we do that? They're breaking this question up. They're really scaffolding this. So what we do is we're just actually doing, like you would at GCSE, sub 3 plus h into the function as if it were x. So f of 3 plus h would essentially be equal to 3 plus h squared minus 4 lots of 3 plus h plus 2. Please confirm in the chat that that's clear. Does everyone get what I've done there? No worries if not, I'm happy to clarify that. But this is just really subbing into a function. Thank you, excellent. Well done if you've shared an answer. I know it's not always easy typing maths into a chat. So I really appreciate that. That's fantastic. But please do, yeah, excellent, lovely. That's brilliant. So what we do now is we just expand that and hopefully be able to express our answer in the form it says. So it's quicker than it looks. Let's sub that all in. Remember, this is a sneaky double bracket. So 3 plus h squared really means 3 plus h, 3 plus h. Don't make that classic GCSE mistake of 9 plus h squared. There's a double bracket there. So there's a sort of middle term coming out. So what you'd get is 9 plus 6h plus h squared. And what we're going to get is minus 12 plus 4h. And what I'm going to do is I'm going to put that in brackets, plus 2. So are we happy that that becomes minus 12 minus 4h plus 2? And then if I tidy that up, hopefully we agree, but we get x squared plus 2h minus 1. And that is in the form that they asked for. B is 2 and C is minus 1. And this notation here, this sort of blackboard bold font of B and C belong to Z. Z is the set of integers, whole numbers. So that just means that they're whole numbers, which they are. So don't get put off by that because you've done it absolutely right if you arrived at that result. Lovely, so that's really good. Now, this was part A of the question, and you might think that's a bit random because aren't we trying to differentiate and we've just done like a little part of it. What we're going to do now is we're going to go, okay, I know what happens when I sub 3 plus h in. Why would that be useful? Let's look at the next bit of the question. This says the curve of equation y equals x squared minus 4x plus 2 passes through the point 3 minus 1. And the point Q, where x equals 3 plus h. Use differentiation from first principles, find the gradient of the tangent to the curve at that point. So what we're doing, the other thing we haven't fully looked at extending to yet, is in differentiation, when you sub x in as a value, it tells you the gradient at that point. Is that something we've seen before? So basically the purpose of differentiation is if I said, right, now x is 10, sub it in, you can tell me the steepness at that point on the curve when x is 10. That's what we effectively use differentiation for. What is the gradient at a specific point? This is leading us through using first principles to do that skill. So what we would have here is we'd say, okay, the way I would do this is it's the limit of as h approaches 0, specifically, I know the x point I care about is 3. So 3 plus h minus f of 3 all over the small change. This is how we apply it to a specific point. Instead of just doing it in x in general terms, we're told we want to know it at the point when x is 3. So we don't need to do it in terms of x anymore. We can sub 3 directly into the derivative. So you might have worked out, well, yes, to those that have said I can just differentiate this and sub 3 in, absolutely. But this question is guiding you through and scaffolding the process of first principles. So we need to do it that way. So if I sub x in as 3 into the formula for first principles, yes, we did use point P because the x coordinate of point P is 3. So we are effectively using point P by putting x as 3. Really good question. So what we would get here is this would become the limit of as h approaches 0. Well, we know from the part A answer that that bit comes out as this. And then we're going to minus 3 subbed into the function. So you might go, okay, I've got to put 3 in here, square it, minus 4 times 3 plus 2. But actually it comes out as minus 1. Why do I know immediately that f of 3 is minus 1? Can anyone spot that? I'll clarify this in a second about the limit and why we're doing this method. But how do I know instantly that if I sub 3 in as x to this function, it's going to spit out minus 1? How do I know that immediately from the question without even doing it? Can anyone see? Point P, excellent. It is basically the y value. The y value is f of x. It's the point subbed in, is y. They gave you it. You could sub 3 in and work out that it's minus 3, but they gave you that. Absolutely well spotted. So I can instantly replace that with minus 1. It saves me doing the work of subbing 3 in. So what I get is when I tidy this up, I basically get, so the limit as h approaches 0, and I will clarify why we're doing this, is going to be h squared plus 2h minus 1 minus 1 will cancel over h. So that will cancel with that and that. So what I get is basically the limit as h approaches 0 of h plus 2, and that will equal 2. So what I've found is the gradient at point P is 2. So what you can basically do is you could, of course, differentiate this without first principles and go 2x minus 4, and then I sub 3 in, and it spits out 2. And that saves all this work from the question. I fully appreciate that. But what it's getting us to do from first principles is go through and plug in 3 plus h and 3 as the point that we're comparing to. We're doing the first principle process on x at a specific x value. So instead of doing it in general and getting 2x minus 4 as the gradient function, we've done differentiation for the point 3 by first principles. So what we're doing is, yeah, absolutely, y is the function of x, y is the output. So what we're doing there is we're comparing y values when I sub that in, divided by how x has changed by a small amount h. And I'm looking at what the gradient's doing for that process. But what I've done is I've specified it to the point at 3 when x is 3. So this is how first principles can be used for a specific point. You don't have to just do it in terms of x and then sub x in as 3 at the end. The point of first principles is you can do this whole process with the point 3 subbed in from the off, and it just produces the value of the gradient. So much like how this question was in terms of x, and we subbed x and x plus h in and tidied it up, this question was at the point 3. So instead of subbing x and x plus h, we subbed 3 and 3 plus h, and the number it produced was that specific gradient at that point. Yes, so the limit is always h tends to 0. That's a brilliant question, because what we're looking to do is close the gap, make the change as small as possible. And so what we're seeing is the gradient is getting more and more closer to its true value at that point. We're closing the gap, closing in on what the steepness is doing at that precise point. Really good question. So for this, h is always tending towards 0 because you're trying to make it specific as possible to that point. Brilliant, great question there. So what we've done is we've looked at what we mean by a limit. We've used binomial expansions to help tidy up some of the problems, do the cancelling out. And then we've talked about it in a sort of a graphical sense as well, and then algebraically. As I said, I know that for a lot of you, and when I was in the position of first learning this, you just want to differentiate it quickly, and you want to know. That is not a problem in that you know what you're aiming for as the answer. That's the great thing, you know what you're working towards. But if it says by first principles, you have to be familiar with this topic. And as I said, it's really key now more than ever because this has been added to the A-level. So it's one of these kind of higher level thinking skills for mathematics that's bringing in some slightly abstract ideas in order for us to really tease out what is going on in the process of differentiation. So that was great. Hopefully that's all clear, but I understand that's a tough topic, and for some people that's very new. Please do a bit of practice on this and check that obviously if you know how to differentiate quickly, you know what the result should be. Yes, so I believe this is on all the A-levels now, and will be relevant obviously in year 13 as well. I want to quickly just talk about Snap Revise and some of the other resources and things we have to offer. So I'm going to quickly stop sharing that. I do want to say thanks very much again for all your work throughout that, and the comments and stuff were brilliant. I'm just going to share this screen quickly and talk you through the resources we have to offer. So on the platform, if you haven't checked it out yet before, please do. Everything has been really geared up for, no worries, thank you so much for looking through the A-levels very specifically, especially as they've changed. So they changed in 2017, and as you guys are aware, they're changing all the time at the moment in terms of the news and how exams are going to be facilitated. but the actual content is the same. The actual content has all been tailor-made, and the resources on the platform are perfectly tailored to every board, to every exam style, every exam point. We've got diagnostic quizzes on every topic, so we can work out what particular skill you struggle with, and then mock papers and really kind of beautifully presented revision resources you can print off and have access to. And we also have weekly web classes. So I'll be running these for year 12 and 13. We work through the whole syllabus, and then we have drop-ins. So if you're struggling with a homework question, or you're struggling with some exam preparation and some revision, you can ask me specific things and I'll work through that with you in those sessions. And these run every week for year 12 and 13. There's also a backlog of web classes if you've missed them and you want to go over a particular topic. And we do all aspects of the course, including the statistics, the mechanics, and the pure. So we cover everything. We cover the whole syllabus. And as I said, the additional thing of having the drop-ins is brilliant, because you can really get that tailored support in terms of the tuition and help you need specifically. So this is, if this is something you're interested in, then please stay tuned for another minute or two. I'm going to talk about how you can potentially sign up and have a little look at this. But please do check out the site if you haven't already. And as I said, the course has been really designed to give really clear exam packs, revision guides, notes on every aspect of the syllabus with really clear solutions, the mark schemes broken down, and the opportunity to quiz yourself at an easy, medium, difficult level all the way through. And so you can kind of take ownership of your own understanding. As I said, the revision notes are just superb and clear, and really bring to life some of the ideas that might be brand new to you. So I hope that's kind of given you a bit of an insight of what the Snap Revise platform have to offer. I'm going to stop sharing that for a second though, and take you back to the PowerPoint. So just to kind of wrap up there, thanks very much again. And as I said, we have got these YouTube sessions running, but weekly we have sessions on the Snap Revise platform. So if you're interested, you may want to look into that and potentially sign up. As I said, YouTube, we have got some upcoming web classes for A-level students. Please set reminders and subscribe if you haven't already. But hopefully they're going to be useful for you going forward. So look out for what we've got coming up in the next few sessions. And as I said, there is a discount. So thank you for staying tuned. If you use this code here, it expires at midnight tonight, and that will give you £10 off your first month. So if you wanted to sign up to Snap Revise, that'd be great. It'd be lovely to see some of you in the drop-ins and the web classes. Then we can sort of further support you with your A-level work. But there's a code for this evening if you are looking to sign up. And as I said, thanks very much for all the work and involvement in the chat today. That was really great, and lovely to see how you were approaching the questions and the sort of different scenarios you brought to light and highlighted as important for the course. So really well done. I'm going to stop sharing that there. Thanks very much again, guys. As I said, we'll be back on YouTube soon with some more web classes, so keep an eye out for that. Keep well, take care, and I hope everyone has a really good week, and hopefully see you again soon at one of these sessions. Well done, guys, and it's been lovely working through that with you. Take care, well done.